Hello students, in this video we'll consider rank 1 perturbations of the identity operator. Let's let T be a rank 1 operator mapping Rn to Rn. Okay, and what this means is the following. It means that T maps any vector u into a multiple of some other vector w, right? So in other words, what this means to be rank 1 is it means that T applied to a vector u has to be some multiple lambda of a vector v. So you're projecting onto this subspace of v, right? And so of course the idea is how do you find this vector v? So in other words, any vector has to be a multiple of v, right? It says the matrix of v, so therefore then the matrix of v, then the matrix of T has matrix that looks like this, some number w, v in the first column, w1, some number w2, v in the second column, all the way down to some number wn, v in the last column over here. And so if that's the matrix of v, because everything has to be a multiple of the vector v, right? So there's some numbers over here in the matrix, w1 through wn. And so this tells us that the formula for this operator T, u, has to be what? Tu is going to have to be v, w perpendicular for that w transpose applied to the vector over here u. In other words, this is the structure of a rank 1 operator, right? So that matrix over there is a rank 1 operator. So that's our rank 1 operator. Okay, great. And so now let's consider the identity plus this rank 1 operator, right? So let's let v and w be given. Let v and w be given. And consider the identity plus v and then w transpose, like that, okay? And let's assume temporarily we can eliminate this restriction. Suppose that v dot w is not equal to 0. They're not perpendicular. So in other words, that v is not in the orthogonal complement of the span of w, right? Okay, good. And so what I'd like to do now is I'd like to find the eigenvalues of this operator over here, right? So in other words, the question for us is what's the spectrum of the identity plus v w perp, right? And so we're going to find the spectrum in terms of finding just what the eigenvectors are going to be, right? So it's very simple to find the eigenvectors. Let's do so, right? So first what we're going to do is we're going to look at the identity plus v w transpose applied to the vector v, right? And so what this is going to be over here is this is going to be just v, identity of v is v, and then plus v, and then w transpose, and then w transpose v. But this is exactly just v plus what? That's just a dot product, so that's going to be v dot w in the direction of v. So this, of course, is just 1 plus v dot w v, right? So in other words, this 1 plus v to w is an eigenvector, and we're going to see it persist being an eigenvector even not without this assumption over here. That's going to be my lambda 1. And now the key is to look at the orthogonal complement of this vector w. So now let's let zeta 1, zeta 2, zeta n minus 1 be mutually perpendicular and the span of zeta 1 through zeta n minus 1 is the perpendicular, is the span of w perpendicular. So it's the orthogonal complement of that one vector, right? This is the orthogonal complement. Okay, great. And so now let's plug in these zetas into the formula over here and see what we get. So if I look at the identity plus v w perp, just w transpose obviously, not perp yet, applied to any of these zetas, zeta I, what are we going to get? We're going to get just zeta I from the identity, and then we're going to have, what? Then we're going to have v, and then zeta I, it's a vector, of course, all these are vectors, right? Okay. Make sure we have our vectors everywhere, right? Vector, vector, right? Vector, vector. Take care of all of our bookkeeping over here. Vector, vector, right? And now what will this give me over here? Well, dot W. But now, these are in the orthogonal complement of W, so these terms are 0 over here. So this is going to be zeta I. And that says that the identity plus VW perp zeta I is zeta I, so that says that 1 is an eigenvalue with multiplicity n minus 1. Great. And so now what we have is we have one eigenvalue over here, and then we have this eigenvalue of 1 plus v dot w, and that's not equal to 0. Now, of course, that's equal to -1. That's going to give me a 0 eigenvalue, so a little bit care has to be exercised over here. But this allows me to get a beautiful result for free, and namely that says the following. It says, in this case, under the assumption that v dot w is not equal to 0, that the determinant of the identity plus v W transpose is just equal to the product of the eigenvalues, so a whole bunch of 1s, 1, 1, 1, 1, and then 1 plus v dot W. So we have this beautiful determinant identity from finding the eigenvalues, right? Now let's suppose in the other case now, what happens in the case when v dot W is equal to 0, right? So what happens in that case, just as a remark, if v dot W is equal to 0, then what haven't we used yet? Let's use u. Then let's let u be an eigenvector of this rank 1 operator. Of VW perp, right? And that would say that this thing, that would say that v and then u dot W is equal to, let's say, mu times u, right? Well, if mu is equal to 0, then that's okay, right? Because if mu is equal to 0, then we just get that this thing over here, then we'll have an, that's going to be an eigenvector of this thing. Then, of course, if mu is equal to 0, then we can just plug in u over here and get that 1's an eigenvalue again, right? And then if mu is equal to 0, then identity plus this thing is going to have an eigenvector. So in other words, that's going to be, so if I plug in the vector over here, u into this formula over here, I'm going to get identity u, so that's going to be a u. And then this thing over here is going to give me a 0, so I get then the 1 is an eigen, then 1 will have another eigenvalue, then 1's an eigenvalue. 1 is an eigenvalue. Right? And if mu is not 0, then what can we say about this? I'd like to look at the orthogonal complement, right? That v and v dot w, right? So what will v dot w be? V dot w, we know that v dot w in this case is equal to 0. And then what can we say now? So we can say that I can divide this over here. That says that mu is equal to v dot v, mu is equal to what we get over here. So we can divide by mu and get that what u is equal to, excuse me. So we don't want to divide by u is not equal to, we can divide by mu. That would say that u is equal to what? Is equal to v and then u dot w over mu. And then what can I say about u? Then this implies that u dot w is going to be v and then u dot w over mu dot w, and v dot w is equal to 0, so this is going to be equal to 0. In other words, this vector u is also in the what? This vector u is also going to be in the perpendicular, the orthogonal complement to w, right? So this over here tells us that u is going to be in the span of w, perpendicular, like that. And so in either case over here, this formula is still going to be valid because now in this case, v dot w is going to be equal to 0. And of course, all of the orthogonal, everything, every eigenvector over here, every eigenvector u is going to be stuck in the orthogonal complement, which means that everything that I plug into this equation over here that's going to give me the orthogonal complement is going to output the formula just 1 in this case. In other words, this formula remains valid even under the assumption that v dot w is not equal to 0 because everything in this case is going to be pushed into the orthogonal complement of w, right? So it suffices to look at this case when v dot w is not equal to 0 because the general form of this formula remains true in either case. Thank you very much.